Hey everyone, welcome to this explainer. Today we're going to take what looks like a completely ordinary, static page of textbook math and turn it into a totally dynamic journey through human history. Because let's be real, math is rarely just about the numbers, right? It's really about the humans who first started counting them.
Now, just take a look at this. At first glance, exercise set 3.1 looks like your standard, run-of-the-mill, maybe even slightly boring homework assignment. But hey, don't be fooled by the academic font. What we're actually looking at here is a fascinating case file. It's quite literally a treasure map disguised as homework, and it's holding four really unique ancient puzzles that we're going to crack open and solve together today.
So here are the four ancient puzzles we're tackling. Number one, the Lothal merchant's trade. Number two, deciphering the Ishango bone. Number three, the limits of natural numbers. And finally, number four, counting on your fingers.
Okay, let's dive right into this with number one. The Lothal merchant's trade, proportional math in the ancient port city. I want you to transport yourself to the bustling, dusty, vibrant streets of an ancient market. Our very first case brings us a specific mathematical dilemma straight from the ancient world of commerce. So, a merchant in Lothal is exchanging bags of spices for copper ingots. According to our text, he gets 15 ingots for every 2 bags of spices. So the big question is, if he brings 12 bags to the market, how many copper ingots is he going to leave with? Take a quick second here. How would you mentally map out this math? Well, here's how this builds systematically. Step one, we know our target amount is 12 bags. And since his exchange rate is based on 2 bags at a time, we first need to figure out how many groups of 2 actually fit into 12. Pretty simple, right? 12 divided by 2 gives us 6. That's 6 groups. Then, step two, for every single one of those 6 groups, he gets paid 15 copper ingots. So we just multiply those 6 groups by the 15 ingots. And the grand total? 90. Our merchant is going to leave the market with exactly 90 copper ingots. It's just a fantastic, foundational example of proportional reasoning. It proves that the exact same logic we use to calculate currency exchange rates today was literally being used by spice traders millennia ago. How cool is that? Moving right along to number two, deciphering the Ishango bone, unlocking prehistoric patterns. For this one, our text points us to a very specific sequence of numbers found on one column of the Ishango bone. Take a close look at these: 11, 13, 17, and 19. What do these numbers actually have in common? Why would an early human deliberately group exactly this sequence together? Well, this brilliantly illustrates the concept of prime numbers. A prime number, if you need a quick refresher, is a whole number greater than 1 whose only divisors are 1 and itself. You literally cannot divide 11, 13, 17, or 19 evenly by anything other than 1 and themselves. The secret to the bone is that these aren't just random scratch marks. They are consecutive prime numbers between 10 and 20. That is just a breathtaking illustration of early human mathematical recognition.
So to completely solve this puzzle, our source asks us to list the next 3 numbers that fit this prime pattern. Continuing upward past 19, the next prime numbers are 23, 29, and 31. It's incredibly profound to realize that we can pick up a logical sequence card tens of thousands of years ago and just confidently keep it going today.
All right, on to number 3. Limits of natural numbers. When the math breaks down. Now, what's really interesting about this slide is how it frames the boundaries of the numbers we use every single day. Natural numbers are our counting numbers, right? 1, 2, 3, and so on. Our text states that natural numbers are closed under addition. That simply means if you add any two natural numbers together, the answer is always going to be another natural number. It's a closed, safe little loop. But look over at the right side. Subtraction is not closed. It sometimes completely shatters this rule. Let's actually walk through a couple of examples to justify this, exactly as the exercise demands. Looking at the first bullet, 5 plus 3 equals 8. Two natural numbers create a natural number. Closed. Second bullet, 5 minus 3 equals 2. Again, two natural numbers subtract to make a natural number. Closed. But wait, look at that last bullet. 3 minus 5 equals, If I only have 3 items, I can't physically take away 5, right? Subtracting a larger natural number from a smaller one is exactly where this whole closed rule completely falls apart. So, the absolutely crucial point here is that to solve a problem like 3 minus 5, you have to completely leave the comfortable, tangible realm of natural numbers. You literally have to venture into and invent negative numbers. The answer is -2, which is an integer for sure, but definitely not a natural number. This beautiful little exercise demonstrates how hitting the limits of basic math literally forces the human mind to expand into entirely new number systems. And that brings us to our final puzzle, number 4. Counting on your fingers. Math in the palm of your hand. Okay, I want you to actually participate with me right now. Seriously, hold up one of your hands. Take your thumb and look at your other 4 fingers. As the text notes, each of those fingers has exactly 3 joints. The exercise asks, how high can you count on one hand using just the joints of your fingers? So use your thumb as a pointer and tap those joints on your index, middle, ring, and pinky fingers. Come on, tap them with me. 1, 2, 3, 4, 5, 6. Keep going all the way across. So what number did you end up on? The answer is 12. You can easily and systematically count to 12 on just a single hand without ever losing your place. It's such an incredible realization, and it really builds the excitement that our very own biology, literally the anatomy of our hands, directly dictated how early humans interacted with numbers. And this brilliantly illustrates the foundation of the base 12 counting system. This ancient numerical system is intrinsically linked to counting those exact 12 joints on your 4 fingers using your thumb. As our source highlights, this specific method was used by ancient Indians, and it's a practice we remarkably still see in the world today. It proves that counting isn't just some abstract concept, it is literally tied to the shape of our bodies. So, as we bring this explainer to a close, I really want to leave you with this provocative thought. How much of our complex, modern world is still built on these incredibly ancient, simple observations of nature and our own hands? I mean, from a merchant trading in a port city, to a human scratching primes on a bone, to the simple act of looking at our own finger joints, these basic actions laid the foundational bedrock for all modern mathematics. A boring homework page is never just a boring homework page, right? It's human history. Thanks so much for learning with me today. Keep questioning the world around you, and I'll catch you in the next explainer.
Thank you.